Today's webinar, we're going to talk about what accelerated live testing is, or ALT. And the good thing about ALT is that it can be really, really powerful. But in many cases, ALT is used as a general throwaway line or concept to allow us to truncate testing without putting too much thought into it. And so for us to really understand what accelerated live testing can do, we need to start by understanding how we get there. Now, many of you who have been part of my conversations in the past, you know that I like talking about failures in a very generic context. We talk about preventing failures. We talk about how we can understand failures. We want to do things to improve reliability, which means we reduce the frequency of failures. And it comes back to understanding how things fail. And measuring reliability can be important. And when I say measuring, it can also mean analyzing. Either way, we're just trying to quantify our understanding of how our things fail. But none of this is nearly as important as designing in reliability. And you cannot use accelerated live testing to make things directly better. It can be very useful, but of itself, it won't help you. You need to have a reliability mindset where you're consistently hunting the vital few ways your thing can fail. And so what that means is that if we look at a device like this smart lock, which is one of the central examples I use in many of my discussions, we might be faced at the initial or the early phases of production, design and production, with at best a baseline configuration like this. And even though this illustration looks relatively complicated and relatively complete, it's not. This is just a simple configuration drawing, initial configuration drawing of a wonderful new device that's going to hopefully dominate the market or otherwise make things wonderful. So how do we make this reliable? Well, let's zoom in a little bit. Look, it's one of the most important parts of our system, which is, in this case, the electric motor, which drives the locking mechanism within our smart lock. And as you can see, our electric motor is connected to our PCB by two cables. In this case, these two cables or wires are connected to each one of these two components using solder joints. Now, don't forget, this is a smart lock, which is going to go onto or into a door. So think about the effects that door slams will have on solder joints. So one of door slams, once this smart lock is installed into a door, there are going to be times when people of various demographics and various ages and various emotional states will slam our door shut. We can't necessarily stop that. It's just how our customers are going to use our smart lock. But that's going to introduce problems for this design as is. These solder joints are not particularly strong. They're not structural. Everyone knows that. But you'd be surprised the number of seemingly mature products I come across, and I know Fred has come across, and I know lots of other people have come across, where mature prototypes still have solder joints because people haven't thought about it. So what can we do? Well, what we can do in this case, for example, is do some really smart things, albeit simple. So one of the first things we can do is include thicker gauge wire to provide more contact area with the motor terminal. So those solder joints that aren't designed to be structural are at least as strong as we can make them be. Then we can have shorter wires to accumulate less momentum during the door slam action. And we can also clip our wires, physically secure our wires, so the shock loads associated with the rapid deceleration of a door slam don't get transmitted to the solder joints. They get transmitted to the chassis of the lock itself through these clips. And then we can also have, for example, socket and plugs at the circuit board, the PCB end of these cables, which are a lot stronger than solder joints and also make our thing much easier to assemble. And we can also do things like introduce incoming inspection of motor solder joints on add that to our supplier inspection checklist. And we can also perhaps do surveillance automated microscopic optical inspections for 10% of incoming motors, where we look at a randomly selected subset of all our incoming motors and do some more detailed and more expensive, more time-consuming investigation. That's why we only do subject it to 10% of our entire components coming in. But that said, that's going to be relatively representative because they're all manufactured in the same way. Now, these really simple basic corrective actions, I hope that you agree with me when I say that they're essentially fast and free and simple if we put them into our first design. So the key for reliability, this is how I make reliability happen, is come up with these wonderfully simple ideas at the very start of the design process, embed them into our first design. And as you can see, you don't need to have too many PhDs or too many years of experience to come up with these really simple design changes. The really complicated, sophisticated design changes for reliability concerns tend to be those that happen later in the design process, where because you've already designed 99% of your system, you need to come up with truly expensive and funky ways of trying to resolve the issue that perhaps preliminary testing uncovered. So that's how we make reliability happen. And the reason why that's important is because you need to understand how your thing can fail before you can even think about accelerated life testing. And that means that you've spent your entire design and production process focusing on the vital few. And these red dots here represent the vital few ways our system can fail. What do we mean by that? Well, if this design as is was allowed to continue operating or continue to be used without any design changes, these are the points where if the smart lock's going to fail, it's going to fail at one of these areas. And so every system will have a bunch of weak points, even the reliable systems. And the idea is that we go through from the very start, focusing on the weak points using things like Vermeers and Holtz and all sorts of other wonderful DFR activities, targeted DFR activities, to progressively take down the next fleet of weak points of our system. And the good thing about this is it gives us a really good understanding of how our thing is going to fail without us even sort of directly trying to do that. If we keep trying to focus on the things that keep us up at night, then we will come up with these wonderful corrective actions in our first design, which not only give us confidence that our thing is reliable, but it gives us a really good understanding of what's left. So now that we have a reliable product, there might be a need to use our understanding of how our system or product is going to fail using the remaining vital few weak points to get a better understanding of reliability in a more quantitative way. So for example, let's just say once we've done this, we want to understand the percentage of smart locks that will fail in the warranty period. So not just focused on improving reliability. Now we've done all the hard work. We want to use our understanding of the residual vital few weak points to estimate warranty period reliability. And in this case, for our smart lock, let's just say a warranty period is 2 years. We'll just focus on that period for this conversation. So that means we're going to analyze warranty reliability, which means try and understand the fraction of things that are going to still be working after 2 years, because perhaps more importantly, that helps us understand the fraction of things that aren't going to be working after 2 years. And those fraction of things that aren't going to be working after 2 years will mean that our customers will be asking us to fix those issues at our expense. That's what warranty is all about. So let's go back to our smart lock. Our smart lock, which has now gone through that robust design process. We've got some wonderful, fast, cheap, free, simple corrective actions embedded into our first design. We then kept reviewing our process, our system throughout the design process as the next set of weak points became apparent. And now we want to understand how likely it is for this thing to fail during the warranty period. So our first approach is to assemble our smart lock, create some prototypes and test 100 of these prototypes for 2 years and see how many are still working after that 2-year period. Now, believe it or not, there are plenty of reliability engineers, so-called reliability engineers out there who believe that this is not only okay, but this is the only way you can characterize reliability. If you can't demonstrate it, so to speak, it doesn't exist. But of course, there's plenty of problems with this approach because 2 years is too long. That means your company is not making money for 2 years. And during that 2-year period of you just testing 100 prototypes, your competitors are now dominating the marketplace. And obviously, once you do these tests, if you do the analysis and you say you found that 8 smart locks have failed in that 2-year warranty period, well, it's too late to do anything about it now because that design team that would design this thing in the first place, that manufacturing team, well, they've all gone because they're not going to sit there next to their computers for 2 years. They're going to be reallocated or retasked to do something else. And all of a sudden, you need to recreate your team from scratch. So we clearly can't sit down with 100 prototypes, test them for 2 years in order to try and understand warranty reliability. So let's go back to the results of our design and production process. We went through that process where we iteratively hunted down the vital few weak points until we got to a point where we were comfortable that we have hunted down enough that to ensure we have a robust, reliable design. And that doesn't mean our system is now devoid of weak points, far from it. Every system has a bunch of weak points, and you can see them represented here by these red circles. So I want you to think of the weak points as the points in our system where if our system is going to fail, where our product is going to fail, eventually it's going to fail through one of these weak points. So let's look at one in greater detail. Well, I got ahead of myself. I should have, not that I didn't rehearse, but delivering this webinar in a hotel means that I'm using a laptop, so I don't have the luxury of having the projection screen or the second monitor that allows me to really get on top of the slides coming up or the animations coming up. So these are the vital few residual weak points, which represent the ways our smart lock will fail when it eventually does wear out. So what can we do with this information? If we look at what we can do is look at each one of these weak points. In this case, we zoomed into, focused our efforts or our attention onto the keypad. Now, the keypad doesn't contain any electronics. There's buttons behind the keypad which allow human beings to essentially input data through pins and what have you into our smart lock. And the keypad itself is simply the rubber covering over these buttons, which amongst other things provide a certain aesthetic, allow the human being to identify which key they're pressing, because each key is now numbered on our keypad, and otherwise protect moisture and dust and other nonsense from getting into the heart of our smart lock. But of course, for whatever reason, after our production process, we believe that we have solved so many problems, but if our smart lock is going to fail eventually, then the keypad is one of the likely ways it will eventually fail if it was used ad infinitum. So let's try to understand the characteristics of understand how long our thing lasts, or perhaps from a more relevant question is, how many of these keypads are going to fail during our 2-year warranty period, which means that we might ask ourselves, how can we mimic 2 years of use? Now, when we say 2 years of use, what does that mean? That's where it's very important for you to have a use case where you understand the temperatures, the humidities, the stresses, everything else that's going to age our keypad. Now, we can see here exactly how our keypad is, at least in principle, intended to be used. Simply, human beings are going to come up and push, from the perspective of the designers at least, random numbers. Designers won't know which numbers are going to be pressed more often than others, or which key is going to be pressed more often than others. And so we need to develop a use case where we try to understand how our users will use, in this case, our keypad. And maybe that use case, in this case, for our smart lock, concludes or predicts that the keypads, on average, will have each one of its keys pressed by a human finger twice a week. Don't forget that keypads for many smart locks are not the primary way of users gaining access. We have many other approaches, including smart locks and Bluetooth connections and all sorts of things, where that mean that the keypad is often the secondary method of ingress or method of unlocking a smart lock. So it doesn't get used perhaps very often, but maybe it does in some scenarios. Either way, you need to come up with a use case which you believe characterizes how your smart lock's going to be used. And so what we could do with this knowledge is then create a finger pressing test rig, which is what this wonderfully sophisticated device is over here. And this finger pressing test rig allows us to simulate human beings pressing these keypads in a very controlled way. That is going to help us accelerate testing. The reason being is we can just simply program our test rig to keep pressing these keypads as often as we would like with certain frequencies. That means we can greatly accelerate the number of times our keys are being pressed every week. So we can simulate finger pressing much faster. However, there's always a catch, and that catch is don't be too certain that we're on top of everything. We need to make sure the pressure is right. We need to make sure that we need to understand how our humans press the keys. Do they do it perfectly? Are there natural oils on the fingertip that make a difference? Does the keypad need time to reset between presses, etc., etc.? So I can see there's a question coming through. William writes that, interesting enough, his in-laws had a failure in this example lock system marketed by a high reputation lock maker, but the lock had failed in multiple of the identified likely failure points. I recognize expanding drawing from the manual for the lock. Obviously did not perform accelerated live testing well and are paying for warranty costs. So just to be clear, William, we actually deliberately created a generic smart lock. So if you do see any similarities between your smart lock and this, that is coincidental. It's much like the disclaimers we get at Hollywood movies. But that said, smart locks tend to have the same type of technologies, and so the designs are relatively similar, which means that yes, you will be able to see some of the failure mechanisms that I'm talking about. And just to be clear, I chose a smart lock almost deliberately because I haven't done any direct work with the smart lock smart lock manufacturer, but the smart lock does contain wonderful examples of different technologies, and all the stuff, all the things I use in my courses are actually products from me running courses with students. So the wonderful corrective actions are from familiar courses I've run with students who've had no previous background in smart lock design. And that just goes to show how you don't need to be an expert to come up with a reliable product, which is one of the many hangups people seem to have. We need to hire a PhD or a Nobel Prize laureate in order to get to the bottom of why our thing is not working. Brian writes that there's things like abuse cases using things other than fingers to press buttons, which is very, very relevant. And I'm glad you brought that up, because in this context, a lot of people, especially post-COVID, don't use fingers anymore. They use keys or they use their knuckles. And so we need to be very careful that we understand how our system is going to fail when we assume that this test rig is going to perfectly mimic the scenario. But let's say to allow this discussion to continue, that we're reasonably comfortable that this thing is mimicking a real world scenario. And now we're going to move into this next phase of accelerated live testing, which revolves around creating a straight line. And then that might cause you to ask certain questions about where this particular webinar is heading. Why are we now all talking about a straight line? Well, a straight line is absolutely vital when it comes to accelerated live testing, and hopefully I'm going to illustrate why. So for our smart lock keypad, you can see that I've created a chart. The horizontal axis represents presses per week, which is analogous to the stress our smart lock's going to experience if we were to accelerate testing. We're going to increase the presses per week, or the rate of pressing, in order to increase the stresses our smart lock's going to experience in a relatively short period of time. On the vertical axis, we have characteristic life, which in this case is going to represent how long a particular prototype lasts under a certain stress regime. And so this allows us, for example, to, the characteristic life is expressed in terms of years. The presses per week is the thing we can control. We can increase the presses per week to decrease the length of time it takes for that particular prototype to fail. But don't forget, the operational stress is down here on the bottom left-hand corner, where we anticipate that a smart lock, when used in the real world, is going to experience on average 2 presses per week per key. So why are we doing this? Well, charts are always a good way to visualize. And here we can visualize 3 accelerated live tests. Each one of these blue dots represents the time to failure for one of our keypads, not the entire smart lock, just our keypads being exposed to our test rig. And you can see here that increased stresses of 100, 150, and 200 presses per week, our keypad took different lengths of time to fail. Time to failure varied. And so this tells us, at the very least, that yes, the stresses accelerate failure for our keypad. There's a problem, and that problem is that the line that joins, or the line of best fit, is not straight. And that is a problem because that makes it very difficult to project back to the operational world scenario, the operational use case. But if we change the scale, as you can see, I've changed the scale on the vertical axis. I might go back to show toggle between the 2 scales. You can see that this is what it was before. Now I've changed the scale, and I've changed the scale in a pretty, hopefully, clever and sneaky way. And it's just one of the first observations associated with changing this scale is that these 3 data points now seem to line up a lot better. This scale is based on the negative inverse of the characteristic life. And we'll talk about why we did that in a minute. But this scale is based on an understanding of how our smart lock's going to fail. And if we understand how it's going to fail, we can come up with these scales. And when we do, we're able to do things like observe that, mercifully, these 3 data points seem to fall along a straight line, which then allows us to project back to the real world operational use case. And then it tells us that in this case, based on our accelerated live testing, that our best guess at failure in the operational use case, or best guess at the time to failure, I should say, the operational use case, is 2 years, which is exactly our warranty period. And that's not good, because that tells us our best guess is that the typical smart lock is going to fail at, or perhaps even slightly before, our warranty period. So we've got some work to do with our design, because this keypad is not able to stand the increased stresses based on our accelerated live testing data. Now, the reason why we want to do this, because instead of taking 2 years to test with our increased stresses, we gathered these 3 data points in no more than 15 days, I should say, of accelerated testing. So that's a little over 2 weeks. With a little over 2 weeks worth of testing, we're able to say something about the likely time to failure in the real world use case. Now, the reason why this line is straight is because it represents a consistent amount of damage associated with these increased stresses. In this case, the reason why we have that negative inverse scale on the vertical axis is that means that if every time to failure occurs after the same number of finger presses, in this case 208, those data points will fall on a straight line. And that means we're assuming that the damage incurred by our keypad is proportional to the number of key presses. If that's the case, that's our model, that's our understanding of how things fail. The negative inverse scale on the vertical axis allows those, will mean that those data points, if they all occur at the same or similar amounts of damage, will appear to fall on a straight line. And we are really good at identifying straight lines. So in doing this, not only have I created a straight line that allows me to predict real world or real use case time to failure, I'm actually able to confirm that the underlying model is correct because we see the straight line. If that underlying model was not correct, where we assumed that the damage is proportional to the number of key presses, then the line would not be straight. And so this is a typical accelerated life chart where we try and skew the scale, skew the axes in order to create straight lines should our underlying model or assumption of how that thing is going to fail will create a straight line, which one, confirms our model is correct or accurate, and two, allows us to project back to the real world conditions. Okay, so I see William's written a couple more things. He's talking about a couple of different failure mechanisms. I think you're talking about in the first question about how key tops tend to fall out when pushed at an angle rather than straight in, which is very important for our key testing, finger pressing rig, which is it's a very valid observation. We often create test rigs which tend to test our product perfectly with the ideal finger press at a perfectly perpendicular angle of attack, which in the real world is not always the case. So we need to make sure that our test rig incorporates that, or at least we somehow try to incorporate that in our testing. And then William also writes that failures, like all natural phenomena, tend to be exponential, making log scale nearly the universal answer. I'm not sure if I agree with that, William, because every phenomena is natural. And if you look at, for example, corrosion, that time to failure is certainly not exponential. Corrosion is very natural, but it's a wear-out failure mechanism, so the hazard rate increases. And happy to talk more about that in separate conversations. And the link between the exponential and the logarithmic scale is not always the case. And I'll show you that through an example later on in this discussion. So, but going back to this chart here, the idea of accelerated life testing is essentially to create straight lines of constant damage, lines of not constant damage, of the same amount of damage, the same amount of corrosion, the same fatigue crack length. The idea of that, we understand our model, we'll see that straight line to confirm our model, and then allow us to project back to the real world conditions. But of course, finger pressing is rather simple, at least to model statistically. Let's say we want to choose the right rubber for our keypad. And that's one of the key decisions that we will often come across when we have to design something from scratch. What material do we use? One that will not degrade too quickly through chemical reactions. So let's go back to our keypad. We might have a choice between peroxide cured rubber and sulfur cured rubber. They might be, in this case, perhaps reasonably equally priced. We just want to see which one is going to be the better choice for us. And because degradation is caused by a chemical reaction, we can use an accelerated life chart which creates that straight line should that underlying model be correct. And a chemical reaction involves reactants turning into products or byproducts. And we'll go into what chemical reactions are a little bit later. But before we do that, let's understand that because not all failure mechanisms are as simple as number of presses, we have to understand how this chemical reaction works to create that accelerated life chart, which will give us those beautiful straight lines. So here is an accelerated life chart for a chemical reaction. You can see on the vertical axis, we have characteristic life, which is scaled logarithmically. On the horizontal axis, we have temperature in terms of degrees Celsius. And you can see that the horizontal axis is skewed in a relative or scaled in a relatively weird way. those red lines are not consistently spaced. Now, let's just say we do 3 accelerated life tests on peroxide cured rubber. And you can see the data points here on how long it took for the peroxide cured rubber to fail on our keypad when tested at higher or accelerated temperatures. The characteristic life on the vertical axis is expressed in terms of hours. Now, you can see that because there's a straight line between those data points, it suggests that, yes, the assumption of a chemical reaction causing the degradation here is correct and allows us to project back to real-world use cases. We can compare this to accelerated life tests for sulfur-cured rubber, and you can see that, yes, sulfur-cured rubber also tends to be degrading due to a chemical reaction. And that allows us to create a straight line, and therefore we can also project its time to failure or characteristic life back to actual use conditions. In this case, it suggests that the peroxide cured rubber will last for 1600 years at 40 degrees Celsius, while the sulfur cured rubber will only last for 170 years. Now, these numbers might seem astronomically big to be irrelevant, but if you have, if it's no additional cost to go for the peroxide cured rubber, that's the one you go for, because that means you'll have a fundamentally more robust keypad. And don't forget, there are all sorts of weird and wonderful chemicals in the world which will accelerate chemical reactions. Who knows what the oils from our fingers will do to these chemical reactions here. So there is a very good reason for us to deliberately chase down the rubber that's going to last 1600 years in our beautiful test lab, because it might not be 1600 years in the real world conditions. So this is how you can use accelerated life testing if you don't have a lot of time. You can see that these data points over here don't take many hours at all in order to be generated. Characteristic life is measured in terms of hours. So the longest test data here involved duration of about 2,000 hours, which is long, but it's also much shorter than a warranty period. But it means we have a lot of confidence in which rubber we are going to use. But be aware that these are only point estimates of the characteristic life, or best guesses, and sometimes we need more than best guesses. So let's look at another real world scenario where we might want to know, for example, the B5 life. B5 life is essentially the time by which we expect 5% of our things to fail. Now, let's further complicate this scenario by saying that for whatever reason, we can't use peroxide cured rubber. They've run out of this rubber, or it's prohibitively expensive. So let's remove that from our accelerated life chart. Now we've left with sulfur cured rubber with a predicted 170-year life at 40 degrees Celsius. And that seems good, but of course, it's a best guess. Some components will fail before 170 years, some will fail after. So we don't want to just rely on our best guess. We want to understand the uncertainty or deviation around this characteristic life or best guess for our operational use conditions. Now, what I might go back, because what we can do is then conduct more accelerated life tests at higher temperatures, so we don't have a single data point at these higher temperatures. When we do that, we get a bunch more data points we can put on our accelerated life chart. And because we know that degradation, at least in this scale, is relatively constant, we can assume with some confidence that time to failure is modeled with a normal distribution in the logarithmic scale. And that means we can perhaps use some statistical tools, which I won't go into in this webinar. I think we cover it in plenty of other webinars, of how you fit a bell curve which you think describes the data best. And you can see here we've fit bell curves which where the center of the bell curves all line up on that central line of best fit and have a consistent spread or consistent deviation each side of that best guess. That allows us to project these bell curves back to the real world conditions. In this case, let's assume it's 40 degrees Celsius. And now we have a bell curve describing the uncertainty we have and the time to failure for our peroxide cured rubber. Now, if we zoom in a little bit on this bell curve, we can, for example, look at this bell curve and say, you know what? This little bit down here, this shaded area, which represents 5% of the entire area under the bell curve, that actually represents the first 5% of our keypads or rubber compounds failing. So that is analogous to those first 5% of failures which define our B5 life. And this is relatively easy to do if you know how to interrogate the bell curve, which again is outside the scope of this webinar. All you need to understand is it's possible to do that. So this is the first 5% of all keypad failures at 40 degrees Celsius based on the chemical reaction associated with the rubber degradation. And now when we push that bell curve and that shaded area back into our accelerated life chart, you can see that that first 5%, that area corresponds with 43.11 years. So that's our B5 life at 40 degrees Celsius in this case. So that tells me, based on our accelerated life testing data, that we would expect 5% of our keypads to degrade within 43.11 years. Now that might be okay. You could also, you look at this bell curve and look at how much area is under that bell curve at 2 years. So this now gives you some information to help you make better decisions about what the warranty period should be, if it's okay, if we need to do more design, et cetera, et cetera. But this is the wonderful, wonderful outcome of accelerated life testing. If we know how our thing fails, we can create these accelerated life charts that allow us to get wonderful information. William asked the question, how far can you push the acceleration temperature till you start having reactions that are not characteristic of the life use case? And that's a fantastic question. The reason why it's a fantastic question is because we often forget about it. We don't want to increase our temperature so that our rubber melts or catches fire. Why? Well, because when we increase stresses, there's a chance we'll change the configuration or state of our product. So if something melts, that's not a failure that's going to be observed in the real world conditions if the melting point is 200 degrees Celsius. There's no way known a smart lock's going to be exposed to 200 degrees Celsius unless it's a fire, in which case that is one of those scenarios where we're not even interested in trying to have our smart lock survive. So we need to understand not only how our thing fails, but how our thing changes. So William asked a fantastic question. And before you even think about turning up the stresses, you need to make sure that those stresses don't inherently change the configuration or state of your system. For metals in particular, you might not see any changes, but you might have some state changes. I might use the term eutectics for the metallurgists out there. It just might mean that microscopic changes will appear if you increase the temperature, which means that that metal is no longer going to be representative of the true use case. Now, Jonathan also writes in the comments, be careful with using the normal distribution as a time to failure distribution. The normal distribution can have a negative values and time to failure cannot be negative. I concur with your observation, Jonathan. However, I need to point out that this is the normal distribution as applied to the logarithmic scale. Because the rate of degradation is constant in this scale, where we have the straight line, the bell curve is often really, really useful. So while I did use the normal distribution as describing what's going on, and I'm not wrong in saying that, but that only applies to this scale. Now, what does that mean? You can see the logarithmic scale on the vertical axis will never approach zero. In fact, what we're using here is the log normal distribution. All the log normal distribution is essentially the bell curve, and the bell curve is in the logarithmic space. But I do want people to heed Jonathan's advice when you're using the bell curve for a uniform scale, i.e. not in the logarithmic space, because yes, the bell curve extends to infinity in each direction, and it can imply a negative time to failure, which of course is not possible. Okay, so that's how we can use this wonderful chart to help us understand when our thing's going to fail. So how do we get this straight line accelerated live chart? It all comes down to understanding how our thing's going to fail, which in this case is chemical reactions. Remember, chemical reactions involve reactants turning into products. And those reactants are essentially materials or substances that exist at a high energy level. We have these everywhere. We invest a lot of energy into manufacturing refined alloys, refined plastics, and et cetera, and that energy means they exist at a high energy state, which is not where they want to be. In fact, every reactant which is at this high energy state, wants to turn into a product at the low energy state in the same way a ball wants to roll down a hill. And when that happens, energy is emitted. The problem for this reactant is that there is this hump called the activation energy, which essentially means for it to start rolling down the hill, it needs to get over this hump, get out of its sort of temporary little status. And then once it gets out of this little, it's over this hump, then it can roll down to exist in the product state. And so for a chemical reaction to happen, we typically need some energy to trigger it. And that often comes from temperature, which is why turning up the temperature will increase the rate at which a chemical reaction occurs. And you will often see energy from a chemical reaction. A good one is a fire. That's a chemical reaction where energy is being released at a rapid rate, and that's where the light and the heat comes from. Corrosion, energy is being released. It's just that it's at such a slow rate. It's not something we readily notice. And so you can see on the left-hand side, we can see an example of a reactant, a beautifully non-corroded, pristine, virgin bolt. On the right-hand side, we can see a product, which is a corroded bolt. And that's a chemical reaction, or a classic case of a chemical reaction. And the more heat you have, the easier it is for our bolt to go from a reactant state to a product state. Of course, there's things you can do, like include put moisture in the air, which essentially accelerates it in a different way by allowing electrical potential to be introduced, et cetera, which is essentially another avenue for energy being input into this little diagram here to accelerate the rate of chemical reactions. Now, a really smart dude was able to essentially model all chemical reactions with this thing called the Arrhenius model. And let's go through this awful looking equation. On the left-hand side, he has this constant K, which represents the rate of reaction. Then he has this thing called the activation energy, which is the height of that hump that we looked at in the previous slide. And that's different for each different chemical reaction. Then we have temperature in terms of degrees Kelvin. And this other K over here, which is confusingly also K, but that's Boltzmann's constant, which helps us understand how energy needs to be imparted to certain molecules and electrons, et cetera, in order to move into a different energy state. And then we have another constant over here, which is particular to each different chemical reaction. So corrosion on one alloy will have a different constant and different activation energy versus to our sulfur cured rubber, which is slowly degrading over time. Now, why am I torturing you with this equation? The reason being is I can replace the rate of reaction with this fraction over here, another constant, and this thing called the characteristic life. Essentially, the characteristic life has an inverse relationship with the rate of reaction. The faster the reaction, the lower the characteristic life, and vice versa, which is why we have this now inverse relation over here. And that constant C allows me to change the characteristic life units. So if I wanted the units to be in hours, C would be one value. If it was in years, C would be another value, et cetera, et cetera. Again, the reason why I'm torturing you is one of the reasons I'm trying to torture you with these equations is to allow me to rearrange the equation, I should say, like this, and then finally rearrange it like this. Now, what you might not be able to easily see is that this is the equation for a straight line. Every one of you might have, so some of you might have heard the equation y equals mx plus c. Y is a vertical axis unit and x is a horizontal axis unit. And if you have m, the gradient, and c, the y-intercept, then you're able to essentially describe any straight line. So here we have a straight line equation, except that y is now on the left-hand side, and it's now the natural logarithm of the characteristic life. So that's where we get the logarithmic scale, the characteristic life. The horizontal axis is always about stress, in which in this case, the stress is about temperature. So we need to have an inverse relationship, 1 over t, or inverse a 1 over t scale on the horizontal axis to make sure that we get a straight line. But we also prefer it if our temperature on our horizontal axis increases from left to right, because that's how human beings like working. We write our numbers down, we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 from left to right, increasing. And so we often use a negative inverse scale to make sure that the temperature is increasing, and we represent it with the scale on the horizontal axis. Just introducing a negative doesn't mean that the line is not going to be straight, far from it. It just means the line, as opposed to going down, now goes up. And so we can use these scales to create what we call the Arrhenius plot. And the Arrhenius plot is the accelerated life chart I showed you previously. Here's a characteristic life in terms of a logarithmic scale, and we use -1 over t scale to create these temperatures here. That allows us to do what we just did. Get accelerated life testing data, alt data, assuming a chemical reaction. See that data on the chart. If it creates a straight line, we can confirm that there is a chemical reaction at play, and then project back to the real world conditions to predict actual use. Okay, a couple of questions. Semyon asks, what is a typical sample size for each stress? For example, is a high stress, is 3 enough? If the lower, is it okay to use 3, or is it preferred to use more or less? Okay, so I think you're just essentially asking how many things do you need to test to get that some of the things, or realize some of the conclusions we talked about. That's a whole different discussion about sample size. For example, if you just want to work out whether the sulfur cured rubber is more reliable than the peroxide cured rubber, then you might only need to have one data point at each accelerated test stress level. If you want to understand the B5 life, then you need to have more data points. If the B5 life is either really close to an unacceptable level, or there's certain other things at play that you need to have more confidence, and you need to have more data points. If the B5 level is an order of magnitude beyond the service life, then you don't need to have a lot of data points. It's all up to confidence. Now, confidence is a measure of use, Semyon, and not a measure of the product itself. So that might not answer your question, but the one thing I will say is that you must always have at least 3 accelerated stresses. The reason being is that if you don't have at least 3, you can't confirm that there is a straight line. Two data points on any chart will always create a straight line. You need to have at least 3 increased stresses to be able to verify, or at least validate, some of the assumptions you're making. William asks, how do we use the B5 life to provide life failure rate for use in system reliability model and system life prediction? The B5 life is not the failure rate, so you can't. The failure rate is one of the most overused and unfortunately detrimental metrics used in reliability, because the failure rate is not reliability. More than happy to talk about that outside of this conversation. There's plenty of webinars and conversations, and Fred actually sponsors a website called knowmtbf.com to hopefully answer some of your questions, where the MTBF is the inverse of the failure rate. So just be aware that B5 Life does not allow you to calculate the failure rate. And I'd suggest you really need to understand what it is you're trying to answer. Okay, so moving forward, if we use Arrhenius plots like this, we don't need to find the constants in that horrific Arrhenius model. All we need to do is understand that this model exists. And as long as we see straight lines on that chart, we know, or I shouldn't say no, we can reasonably conclude, or conclude with some confidence, that the chemical reaction model that Arrhenius came up with is at play. And that allows us to create that straight line, which then projects back to the real world conditions. And you never have to find these constants. That's one of the beauties of accelerated life charts, including the Arrhenius model, Arrhenius plot, I should say. But you need to start with understanding your decision. So if you're interested in improving reliability, that's one thing. If you're interested in measuring reliability, that's another. That's where accelerated life testing usually exists. So improving reliability is about finding those weak points that you then might subject, those vital fields, you then might subject to quantification tests like accelerated life testing that help you understand how long it's going to take before your system fails. Now, the improved reliability tests are always faster and cheaper. The measuring are always more expensive and take longer. And the reason why I'm talking about this now is because there are tests that help us find, for example, or give us a prioritized list of the weakest parts of our system. Now, you can see here that we might have subjected our product to a test, and the test came back and it said, hey, the weakest part of your system is the fan mounting bracket. Now, these sorts of tests, which help us understand the weak points, are fantastic for improving reliability. The reason why I'm talking about these ones is because these sorts of tests are often called highly accelerated life tests, which sound a lot like accelerated life tests, but they're not. HALT and ALT are very different, even though their acronyms are very similar. Now, HALT is all about essentially trying to, in a non-scientific but controlled way, increase the stresses that products like, in this case, the laptop, are being exposed to in order to find those weak points. So this is a HALT testing chamber, and you have a technician who sits next to the HALT testing chamber and runs a series of tests where they increase the vibrations. There's 6 degrees of freedom as a rule, and we have rapid temperature increases, decreases in order to expand and contract joints, so on and so forth. And the reason we want to do this is try and find all those structural weak points that are going to ruin the day of our system. As a rule, we never do it on a final product like this. It's just a promotional video. We tend to do HALT on components like this PCB. You can see it's a very slow motion video of a PCB in a HALT test chamber. Just shows how violent the vibrations are. It almost looks like an earthquake in San Francisco. Sorry, Fred, I know that's a bit close to home, but it's not a bad analogy. And you can see that in this particular video, the capacitor on the left is in a lot of trouble. You can see it's a bit wonky. It's leaning to the right, and very soon it's going to come flying off. Now, that tells us that the weakest part of this PCB is that capacitor. And so what will happen is that capacitor will be then essentially secured firmly back onto our PCB, and then the tests continue until we find the next weak point. So even though HALT and ALT sound very similar, they're very different. HALT can't tell you how reliable your thing is. It can tell you what the weak points are that allow you to do things like use accelerated life testing to create data points which help you understand time to failure. But if you want to have a bit more confidence, you need more data points, which is why accelerated life testing is always more expensive than HALT. HALT can be done in a matter of days, and accelerated life testing often requires weeks and special chambers. But that said, it can be very inexpensive compared to, for example, old school demonstration testing, where you get those smart locks, put them indoors and just test them for 2 years. So ALT is a lot faster than that sort of archaic form of testing. So understand what it is you're trying to do, and that will help you understand how you use ALT. ALT can help you find those weak points. ALT can then quantify how long it will take before those weak points cause failure. So design decision making is all about conducting tests to improve reliability, and measuring reliability tests are all about business or regulatory decision making. And that's not a hard and fast rule because, for example, we showed how accelerated live testing can help you delineate between two types of rubber. And that is obviously a design choice and therefore going to improve reliability. But if you're in it to try and characterize, for example, the warranty reliability of your smart lock, then now we're not improving the design anymore. We're trying to measure it to inform our business decision making. So measuring reliability can be important, but it's not nearly as important as making or improving reliability. And that needs to be the first step, because if you don't know how your thing's going to fail, then you don't know how to create an ALT chart. William asks, HALT and reliability growth. I dare say you're just fishing for comments about the relationships between the two. So HALT is essentially controlled but not scientific increasing stresses in order to find the weak points. Reliability growth, especially reliability growth used by militaries and people who follow military standards, it's all about testing to find the weak points, but without increasing the stresses. So HALT test chambers will essentially try and torture those components until they break to find those weak points. Reliability growth used in the context I described is all about, for example, getting a military vehicle and driving it along a test track, observing a failure, designing that failure out of the system and where you keep on going. So reliability growth takes a long period of time. And because you're testing the entire system, you're not focusing on specific failure mechanisms like we did for the keypad that allowed us to create an accelerated live test plan, which means that the reliability growth I believe you're talking about takes so much longer than an accelerated live test. There are times and places for reliability growth to be used, but I often find that reliability growth is used as a panacea for reliability concerns at the cost of time, money, sanity, and lots of other things as well. So I hope that answers your question. See in the chat, there, I can see that Fred added the link to knowmtbf.com. Brian states, also need to make sure the failure modes are relevant. For example, with gear testing, increasing the load can result in spalling, which might never be experienced in normal customer usage. Fantastic, Brian. Thank you for that input, because you're 100% correct. You're essentially not only changing the configuration, you're creating a brand new failure mechanism, which is not going to be observed in the real world. And so what you're doing is reminding me and everybody else that we have to understand how our things are going to fail, and perhaps also understand what needs to happen for our things to work. So some really good insight from both of you there. So it comes down to decision making. Before we even think about doing ALT, what are we trying to do? And there are lots of different decisions that young reliability engineers and old reliability engineers alike need to need to understand. Is nothing reliable enough? It's going to break. What is reliable enough? What is the goal? What do I need to do next? Because depending on which decision or which question you're trying to answer, you need to potentially have a different test approach. ALT is not the answer. It is one answer that you might decide to employ or might use to help get the information you need for a decision. On that note, are there any questions? I notice I've gone straight through the entire hour. I'm more than happy to hang around and listen to questions and answer questions until we're done. But if those people need to spear off straight away, thank you for your time today. Much appreciated. Please let us know what we did well, what we didn't do well, and let us know if there's any advice or requests for future webinars. Okay, I can see a couple of questions and chats coming through. William asks, how to sell HALT to management? I'm going to have to defer that question to perhaps the end, William, because this is a webinar about Holt and not Holt, but I'm more than happy to engage with you outside this forum. A Holt is a wonderful tool for certain scenarios. It's not the tool for all scenarios, but the idea is that management get invested into Holt when they can understand that it brings forward all those defects, or brings forward the discovery of all those defects, which would cost hundreds of millions of dollars, so to speak, later on during the production process or in the hands of our customers. So if you need to speak to me more about that, I'm more than happy to, or just ask or do it outside of this forum. All right, lots of stuff coming through in the chat window. Okay, oh, not questions, just thanks. What happens when your products last beyond the capability of the Holt chamber? Now, a good Holt technician will proudly say it has never occurred on his or her watch. Of course, it does in some cases, not everything fails. But the idea is that if you do have a product that lasts beyond the capability of your Holt chamber, then you just need to investigate how your thing fails in a different way. As a rule, that scenario is quite rare, and I wouldn't invest too much time planning for such a scenario, because there's always a way you can break something. You need to do it in a controlled way, but you can do it. Thanks, by the way, for all those people reaching out saying wonderfully positive things. Jing Song says, I know some people call such predictive tests accelerated lifetime tests, and completely, from my perspective, I do not get hung up on terminology. I know some people do. If I walk into an organization that insists on using accelerated lifetime tests as the label for these sorts of tests, I will more than happily follow that line, because it's not important, or it's a waste of time debating about what you call things. It's all about how you go about achieving things, because at the end of the day, it's the same process. We use models like the Arrhenius model to understand how your thing fails to create those life charts. And of course, there's lots more models out there than just chemical reaction models. There's things out there like the Eyring models, the Eyring models, depending on how you pronounce it. You can accelerate fatigue if you know the SN curve of that particular alloy, etc., etc. So there's hopefully that hopefully answers your question. That I don't really care what you call it, as long as you understand how to make it work. Thank you for your feedback, everyone. We don't want to over-engineer our products. Kenneth, completely agree. In my tutorial here at RAMS yesterday, I made a distinction between over-engineering and reliability engineering. Over-engineering is what happens when people don't have the confidence that their thing is reliable, and they don't have the skills to make it reliable. So they make everything twice as big, twice as heavy, twice as cumbersome, with the hope that it's going to last longer. But that's not, we can't afford to do that these days. If you look at a smartphone, the space allocated to components inside a smartphone is increasingly tight. So we have to always exist on the margins. What about tools, techniques, and use in conjunction with ALT, like DOE, margin testing, stress strain? Oh, there's a lot to unpack there. But again, comes down to the decision you're trying to inform. DOE, for example, is what you might use if you don't understand how your manufacturing process is failing, or how your thing is failing in the real world. So DOE is all about understanding what levers to pull to essentially control the way your thing fails, which is different to ALT. ALT is all about knowing what levers, how your thing is going to fail. You're just trying to increase a stress in a very considered way in order to characterize it. DOE is usually about discovery. Margin testing is relatively similar in that it's trying to characterize or measure reliability, but it does it without accelerating stresses. It's all about room temperature, operational conditions, which are the antithesis of ALT, in that we don't accelerate our observation of failures. Michael asks, any upcoming or past webinars on HALT testing? I think we have a past webinar on HALT. If not, we can fix that. Thank you for that request. If there's not one in the history of of Ascendo, we can put one up. So thanks, Jonathan. I do see you're a UMD graduate, and you read a certain very boring book that Three Lunatics wrote. Marcel asks, how can you access the presentation review? And I believe Fred has already answered that question. Hope is not reliability improvement strategy. Hope is never a strategy. Hope is an emotion, as is rage and anger. And then you'll usually have hope followed by rage and anger if hope is confused as your strategy at the very confused to be your strategy at the very start. So I furiously agree with what you're suggesting there, William. Okay, go back to questions. I don't see any more questions. And we are now down to half the attendees remaining. So I can see we're slowly trickling out. I'll give you guys a couple more minutes to throw questions my way. There's obviously a lot more to accelerated life testing. I didn't talk about acceleration factors and other sorts of things because today was all about just understanding the concepts. And to be honest, understanding the concepts is way better than understanding the acronyms and getting the titles right. Sorry, Fred, I'll ask out loud. Do we have a whole webinar that we've done in the past? I'm trying to remember if I've done one. I know there's plenty of content on HALT on AscendoReliability.com, so it won't be too hard for you to learn about HALT.
Yeah, I do think we have one. There's it's over 100 different webinars now, and without going through the list and tracking down that particular one, leave that to the curious.
Yeah.
But there's plenty of actually, the first Speaking of Reliability episode 1 was with Kirk Gray and myself, and we talked about HALT. And I think we've talked about HALT and HALT testing and strategies for doing it and uses for it numerous times within that podcast series. Kirk has got a handful of articles up there that go into more depth under the articles tab, under accelerated testing, I think is the name of his series. And it sounds like it might be a hot topic for a future webinar, is to go into the concept more closely like you did for the ALT.
Yeah, I think so. So we might add that to the list. So stand by when most of our webinars and articles are in response to requests or ideas that are thrown our way. So it's up to us to make sure we satisfy or scratch that itch. So yeah, stand by. I'm sure we'll be on top of it sooner rather than later.
All right. I think we've exhausted today's group. We'll be back next month, Chris, with another webinar. My webinar that I was going to do 2 weeks ago got canceled due to weather conditions here locally for me. So we postponed that. It's the status of reliability engineering or education, professional development.
Right.
That kind of stuff. So I'm well prepared for that. I have to probably look at it again, figure out what I was going to talk about.
But I just see that William asked one last question. Will the slides be available? William, just there will be an accompanying guidebook uploaded by Fred really soon. So I don't do PDF slides, that you get a guidebook that accompanies the webinar. And of course, you can review the webinar at your leisure in the future. Yeah,
and it's on AscendoReliability.com under the webinars tab. Click through that, and then there's a section just for the Ascendo Reliability webinar series, and you can find it'll be posted, maybe not today, but within a day or two up on that site.
All right, Fred, I think we're done. Hopefully we answered a few questions and improved the lives of at least one reliability professional somewhere.
Yeah. All right. Well, thanks a lot, Chris. Talk to you soon.
Thanks, Fred. Always a pleasure.